Today we're starting a new unit. It is our logic unit. We're kind of backtracking a little bit. We're going to the second chapter of the book. The first day of notes for this is called, as you can see, conjectures and counterexamples. So we're going to start with a little bit of vocabulary to get us started. The first word that's going in there, and the space isn't very big, so bear with me, is inductive reasoning. Hopefully, you probably can't see that very well, but hopefully you got the sound on this. Inductive reasoning, and we're going to say that is reasoning that uses a number of specific examples to arrive at a conclusion. So you might do stuff like this in other classes, in science classes, anything that you're basically coming up with a conclusion at the end. My steps to do it: I observe data, I recognize patterns, and then I make a generalization about those patterns. The conclusion that I'm coming to using this inductive reasoning is called a conjecture. So we're going to practice a little bit with what it means to make a conjecture and kind of how I do that. So this first example that it has here, science, says a scientist dips a platinum wire into a solution containing salt, passes the wire over a flame, and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt, finding that they all produce an orange flame. Make a conjecture based on her findings. So again, I'm looking at what this scientist is seeing, and she says that she's seeing every time that she has a solution with salt in it, when she passes it over a flame, it produces an orange-yellow flame. So a conjecture that I can make based on the data or observations that I've gotten here is that salt produces an orange-yellow flame. Now obviously this isn't very mathy, but it's just getting us in the mindset of what it means to use inductive reasoning to make a conjecture. Another example of that is if we look at number 2, it gives us a sequence of numbers and it says what is the next term in the sequence. So this goes back to one of the first things we said in these notes about recognizing patterns. If I look at this set of numbers, I just want to look to see what's happening between them. And you've probably done this in other instances, in other classes. Basically, if I want to look between 3 and 6, 6 and 9, 9 and 12, what's happening there? This is a relatively simple example. For each of these, I'm just adding 3 to get to my next number in the sequence. So my next term in the sequence, if I add 3 to 15, is going to be 18. Okay, and when you look at these, I try and look at kind of every possibility I have. If I take the first term, can I multiply it by something to get the second one? Okay, can I multiply it by that same thing to get the next one? To kind of do a process of elimination. So for the next one, what are the next 3 terms in the sequence? 2, 4, 7, 11. It's probably easiest to start with adding to see what's happening between there. If I go from 2 to 4, I'm adding 2. From 4 to 7, I add 3. From 3 to 11, I add 4. So if I'm going to make a generalization about this, I'm going to say that each time that I go to the next term, I add 1 more than I did the last time. So if I added 4 to get to 11, to get to my next term, I'm going to add 5. So it's going to be 16. To get to my next term, I'm going to add 6. So I'll have 22. And then to get to my third term, they asked me to go 3 more terms, I'm going to add 7. So I'm going to end up at 29. So the next 3 terms in my sequence, or my conjecture, is that the next 3 terms are going to be 16, 22, and 29. Easy enough. Oops, didn't lock my screen. It'll be okay. Okay, next example they give me, what's the next term in the sequence? They give me a hexagon, pentagon, and square. Let's think about what I know about those 3 things. I know that a hexagon has 6 sides. A pentagon has 5 sides. A square has 4 sides. My mind's immediately going to, okay, I'm going down by a side with each of these. The next term in my sequence is going to be a 3-sided figure, which I know is a triangle. My conjecture is triangle. That's going to be my next term in this sequence. Another one with numbers. Next term in this sequence. I go from -1 to 2 to -3 to 4. I'm noticing a pattern here that my digit is going up, but I'm alternating between positive and negative. So if my first one's negative, my second one's positive, my third one is negative, my fourth one is positive, my next in the sequence is going to be negative. And I said my digit's going up by 1 every time. So it's going to be a 5. So my conjecture is -5. Now I want you guys to try these next two. It gives you a sequence of shapes, and it says draw the 25th shape in the sequence. A couple things you want to look at. There are a couple ways that you can kind of start looking at this. I can label each of these. Notice what's happening on the odd ones, what's happening on the even ones, how many times it takes to go through a cycle of repeating a pattern, things like that. So see if you can come up with what the 25th shape in the sequence would look like. And then also, I believe on the back, it asks you to describe the 30th shape in the sequence. So you don't have to draw it, but just describe it. So pause the video for a second and see if you can get that done. Okay, now that we are back here, let's take a look at this vocabulary, another vocabulary term that is going to be important to us. It says a blank is an example that proves a conjecture to be false. What I'm putting there is counterexample, which might be a word that you have seen before. I think the best way to think of it is think about this counterpart. If you're think about like getting it, if you're in an argument with somebody or something like that, basically my comeback to an argument is called my counter argument. If they say something to me and I'm trying to disprove it, I'm going to come back with a counter argument. So here I'm going to say a counterexample is an example that proves a conjecture to be false. As we have learned in doing proofs, it can be a little tough to be able to prove something is true. But it is much, much easier to prove something is false because I need one single example, being the counterexample. So the example they give here, I want to buy a new truck and I've been looking at the new Toyota Tundra and every one I have seen is gray. It says right there, to prove something true is hard. If my conjecture, that generalization I make, is that all Toyota Tundras are gray, how am I going to prove that? I haven't seen every single Toyota Tundra in the world, so I have no way of really proving this, unless I do find every single Tundra in the world and do in fact determine that they are all gray. So this is very difficult to do. However, if I go down here to prove something false is much easier. I'm doing the same conjecture. I'm saying all Toyota Tundras are gray. My counterexample, however, if I look out in the parking lot and I see a Tundra that is red, I automatically know that this conjecture is false because I have one single example of a Tundra being a different color, so I know that that's not true. So let's take a look at a couple of these down here. Example 4 says conjecture. If n is a real number, then n squared is greater than n. That seems to make sense. If I take any number and square it, it's going to be greater than just that number. But we have to think about real numbers is any number that can basically be plotted on a number line. So I'm going to start with the most basic example 1. If I say n equals 1, n squared is greater than n, 1 squared is greater than 1, that would say that 1 is greater than 1. That is not true. So that one example proves that that is not a true statement. So I'm going to say this is false. The next example says if jk equals kl, then k is the midpoint of jl, true or false. Now this one's a little bit trickier because we kind of have to think about in terms of shapes and where can jk and kl fall, because it doesn't really tell me what JL is. It doesn't tell me if it's a line segment, it doesn't tell me if it's a ray, it does not tell me anything. All it says is JK is equal to KL, and I'm looking at JL. A counter example, for example, that I could give is if I put them in the context of this triangle. J, K, L. I can still say that that's true. That gives me an isosceles triangle. But K is not the midpoint of this. K is one of the endpoints of each of those sides, but I cannot say, regardless of if those are equal, that K is the midpoint of JL. So that one is also false. And the last example that I've got on here, on his way to the local hunting and gathering convention, cave person Stony Grok picks up a rock, drops it into a lake, and notices that it sinks. Okay, so that's a little observation that our friend Stony Grok, or Grok, I don't know, okay, picks up a rock. He picks up a second rock, drops it into the lake, and notices that it also sinks. He does it 5 more times. Each time the rock sinks straight to the bottom. Stony conjectures, or again, generalizes. I don't know. I think that's meant to be funny. I don't get it. So forgive that. Which translates to, basically we're just writing our conjecture here. His conjecture or generalization is probably going to be that all rocks float. So what I want you to do, you try this. What would a counterexample be that he would need to find to disprove or at least refine this conjecture that all rocks float? So that's the last thing I'm going to have you do in this video. So try and get that done, and we'll talk more about some of this stuff next class.